Hey, welcome back. This is Josh. I wanted to work on some scientific notation today. If you're familiar with the idea, I just wanted to give a quick background, so I guess just deal. So usually this is presented in different ways. I try to give it my own little spin and just talk through it as I'm presenting this to my students. And so the way I like to do it is I just talk about how, back in the day when people were counting things, whether it was distances between planets, so like massive numbers, or huge amounts of dollars and currency, or maybe it was how many grains of sand are at the beach. You're talking about things that are so big that do we really care about that last grain of sand or that final dollar? And usually my students will say, of course, like money is money, right? But let me give you an example. If we had a number that was like 7, 4, 2, 3, 8, 9, 4, okay? Let's say this was the amount of dollars that you had, right? And so I always present it like this to students, and I say, if you had $7.4 million, would you really notice if your best friend asked for $4? Would you really be that type of person to say, you know what, I loaned you that $4 a while back, can I have it back? And that's not really the case. I mean, if I had $7.4 million in my pocket, the last thing I'd be worried about is that last $4 that might have fallen out when I grabbed my wad of cash, okay? Same thing with grains of sand. If I was counting grains of sand, I'm sitting there for weeks and weeks, and I've counted 7 million grains of sand. Am I really worried about that last 4 grains of sand? Is that gonna really drastically change what I'm doing? Not so much, okay? Now, granted, if this was like space exploration, would I need to know how many miles it is to the next planet? Yeah, I would, and I'd probably want to know down to the last mile. But at the same time, if I was just talking general numbers of like how far it is, you wouldn't need to go out this far. I mean, okay? Same thing with like amount of bacteria that's growing at a certain rate. You don't have to really be that specific, because some of these things are so massively large or infinitesimally small that, that last bit, it just doesn't matter. I mean, this thing is so big or so small, it's negligible, okay? So getting back to this, there's 2 different ways that they're gonna ask you to work on this, okay? They're gonna ask you to write things in scientific notation, and then they're going to call the other version standard form or standard notation. A lot of books do it differently. I personally like standard form just because I don't want both words having notation in it. I think it kind of confuses kids at times, or students, I should say. But we have scientific notation, and then we have the standard form. And you could look at these as kind of like opposites of each other. Okay, I'll put an equal sign. I guess you could put a slash through it to show that they're like not equal, but it's kind of like the opposite of this thing. And so let me do a couple, and then maybe that'll start to make sense. So first we're going to start with converting things into scientific notation, and then we're going to do a couple where we go back to standard form. I guess I can leave that up here. Let's start with this guy up here. 6,435. And again, I think this is a good one where if you wanted to watch a couple of these and then go back or pause the video and maybe try the last couple on your own, then go for it, and then kind of see where you're at. So this guy, scientific notation. Every book teaches this differently. Online courses that I've seen teach it differently. I try to go with the most standard format, I guess you could say, that's kind of the most commonly used, which is this: number, decimal, number. Okay? And I encourage my students to write that down because I think it's going to help you remember exactly what needs to get done. We got to convert this guy into number, decimal, number times 10 to the something. Okay? This is kind of like a standard frame that you could use every single time. And I encourage that, right? In all my other videos, I'm always like, dude, if this is going to help you get it right every time, why wouldn't you do it? And then maybe, you know, I don't know, a year from now or whenever from now, if you get good enough to where you're stable at this, then yeah, you probably don't need to write this out. But in the beginning, I think it's helpful. It gives you a good visual and it reminds you of what needs to be done. So when we have a number like this, you know, we don't say it, but there is technically a decimal here. And maybe some zeros after it, right? Let's say this was dollars. There technically is a decimal at the end of this, which allows us to know how many units this actually is. And in order to figure out how to put it into scientific notation, we need to have it in this format where we have a number, then a decimal, and then two more numbers. And some books will let you drop off that last one, but we'll get to that in a minute. And so the way you do that is you say, okay, well, I have this big old number here. I'm just kind of moving that out of the way a little bit. And I want to get it to number, decimal, number, okay? So we know the 6 is going to drop to here, and we know the 4 is going to go to here, and the 3 is going to go to here, because that's the starting number that we were given. But in terms of figuring this out a little bit further, how do we actually make that happen? Well, we move the decimal point. 1, 2, 3, okay? And I always draw these loop-de-loops in class, and I think these are good reminders. Like, why wouldn't you set yourself up for success? Okay, so if you move it 3 times, then that would be the number that we would place up here in the exponent box. Okay, so far so good? All right, this is pretty straightforward. I'm going to leave this one up here while I do this guy, and just so that we can kind of talk through both of them at the same time. So 897, okay? What is our goal? Scientific notation, right? How do we write it? Just like this. Number, decimal, number times 10 to the something, all right? And so we know that, you know, this is our first number, so that's going to go there, this is going to go here, this is going to go here, so it's 8.97. And then we got to talk decimals, right? We know that there's a decimal point here. Oh, that marker's done. I'll use red. So we know that there's a decimal here, and we know we need to move it to this spot in between the 8 and the 9. So we go 1, 2. All right, that would be our 2 movements of the decimal place. And so because we're moving it twice into a big number here, we need to notify that or notice that or write that here as a 2, okay? Because that's how many times we moved it within this big number. And so things start getting a little bit trickier as we start moving down this, but I'm hoping that this part here makes sense, okay? The goal is just to figure out what is the first digit of our number, and that would go here, and then we just start moving across. Now, you might notice that this 5 here just kind of disappeared, right? And that gets back to that big number that I wrote before, that 7.4 million, right? You're not worried about this last number. If you were to expand this out and write it in standard form, you would have 6.43 times 10 to the 3rd, okay? This is telling you how many times to move the decimal to the right. So if we needed to write it and go backwards into standard form, we would go back 1, 2, 3. Now there's nothing there, so I'm just going to put in a 0 as a placeholder. But that again gets back to the fact of, like, if you had 6,000 crickets, let's say you were using them for an experiment. If you had 6,000 crickets, are you really worried about that last 5? Are you going to be like, oh my gosh, those things got away? No, you'll probably be okay. And so that's where, you know, you put in zeros as fillers or placeholders so that you can get back to your original number. But the 5 really is really not that much when you're dealing with 6,400 of something. Okay? All right. So I'm hoping it's starting to make sense. This is kind of the basics, and then these last couple get a little bit more complicated. Actually, let me get this out of the way because I want to write a little bigger. Let's see here, 452 times 10 to the 3rd, okay? So they gave you something over here, kind of like it's in scientific, but is this guy in number, decimal, number format? No, it's not. So we need to put it into scientific notation. So we know that there's a decimal here because this is a number here, and this is the end of it. So we move it over 1, 2. We write our number in here, 4.52. We had a 3 there. I moved it 2 more times, so I can just add those together. And now I have a 5. The next one is a little bit different because now we have a small number, 0.2496. Okay, write it in scientific notation. Okay, I need to do the same thing. Number, decimal, number, times 10 to the something. Okay, I need to move the decimal into this middle spot right here, right? That's going to be where I need to go. So I end up with a 2.49. And then how many times did I move it? Once. So I put a 1 here, right? Well, not really. Okay, this is where it starts getting a little tricky. When the numbers are really big like this, you just figure out how many times you moved it and you go with a positive value. But when you're dealing with decimal points and then a big, like a super long small number or something, then you have to make sure you take that into account. So yes, you're moving the decimal to the right, but you do need to add something which is going to tell us, well, let me show you. Let's do this. The answer is -1 here, okay? And so if we were to think of it as a number line, positive, negative, okay? In order for us to get this direction, we would have to move to the right, okay? So far, so good. But in order for us to write this number out in standard format, let me rewrite it again. Let's say I was given 2.49 times 10 to the -1, and they said, hey, Josh, write this number in standard form, okay? This positive or negative right here is going to tell me which direction to move the decimal. So to write it in standard format as like just a number, I would have to move it 1 space, but because I have to move it 1 space, if I have to move it this way, positive, I'm just going to make the number 24, and that's not right. I have to be able to move it this way to make it 0.249. And so this negative sign, if it helps you, think of it this way. Okay? You're going in the negative direction, so you're going to be moving it this direction. Okay? It's a really weird concept. It's probably one of the trickiest parts of scientific notation, is just which direction do I move the decimal. Okay? If you're solid on the positive numbers or the big numbers here, and you're just moving it to the right every single time because you have this number that's like 8,000 or 9,000 or 40 million or whatever, then great. But if you see a decimal, maybe even if you just want to tell yourself, hey, anytime there's a decimal, I know I got to move I know I have to move it so that I can make it into number, decimal, number. But when it comes to getting back to where I wanted to start, I'm going to need a negative sign next to the exponent. It's kind of tricky, I know. Let's move on to the next one, and maybe I can kind of talk about that one more time. Let's see. Let me get rid of this and this. Okay. So this one is when I always try to trick my students. Well, not really. I just try to throw them a curveball and see where they're at, okay? We're multiplying. I guess you could almost look at this as 2 binomials, but we're going to multiply parts to parts, okay? And when I say that, I mean we're going to multiply the 7 times the 4, which is 28, and we're going to multiply the 10 squared times the 5 squared. And getting back to my other work, if you want to get technical with it, we could look at this as a squared times a to the 5th, which is the same thing as a times a, right? Times a times a times a times a times a. And because they're all being multiplied with the same base unit, we just add them all up. So 1, 2, 3, 4, 5, 6, 7 gives us times 10 to the 7. Now you might be saying, oh my gosh, Josh, why don't you just add the 2 exponents together? Yeah, you pretty much can. But I just wanted to, for all the algebra people, I just wanted to kind of remind you that this is kind of the rule that we're using. So it isn't just this arbitrary, when you see this, you just add them together. There's actually math behind it. So 10 squared times 10 to the 5th is 10 to the 7th. And the reason I multiplied this times this is because they're like terms, okay? It's just like as if they were A's, just like these guys are both numbers, so I can multiply them together. So a lot of times when I'm teaching this, my students get real excited and they go, yes, that's the answer, I'm done. And then I always say, oh my gosh, you were so close. You needed to do this one last thing. And then they ask what? And I say, well, and that's usually when I'll write out on the board that, which is the same thing I've been showing you on all these problems, but anyways. And usually the light starts to click, or, you know, the switch, and they go, oh, that's right, this is not in scientific notation. And so it's a very common way for you to make a mistake on a test or on a homework assignment. You've done all the work and it looks great. It's just that you just need to do one more step, which was take this 28 and make it into a scientific notation format with this guy as well. So you move the decimal over one more spot to make it 2.8. If you don't have a number here, that's okay. Some books will ask you to put a 0 there as a placeholder. Some books will just let it go at 2.8. I was taught number, decimal, number, but you know, if your book's okay with you just doing that, then so be it. So we have 10 to the 7th, but because we had to move it that extra time, we have to add that in. We have to add in that extra movement to make the number even bigger. So instead of 10 to the 7th, it's going to be 10 to the 8. All right? It's just one of those tricky things, and it always comes up, and I usually try to throw these out there and show my students, because when you multiply these two numbers together, if you get a bigger number like this, or even bigger, you got to move the decimal even more, because your answer is just some big old answer. It's not an answer in scientific notation, which is kind of the purpose of the lesson. So watch for that. All right, let me clear this stuff out of the way. Where are we at? Down here. Okay, so these ones I just wanted to go the other direction, back into standard form, standard notation, whatever you want to call it. A lot of books teach this in different ways. 2.35 times 10 to the negative 3. So this again gets back to that whole 0. Oops, that's kind of sloppy, but that's okay. Plus minus, right? This is going to tell us what direction we need to go. Okay, and that's why I draw the number line up there. Again, visuals. If this is going to help you learn this stuff, then draw it on the board. Like I draw it every single time because it helps me. Why wouldn't you draw this kind of stuff on your paper to remind you what needs to be done? Okay, well, it's already in number, decimal, number, and this is the extra part. And it's already in scientific notation. So we need to convert it back into like an actual number. I guess that's what you could call it. And so we know we're going to move the decimal. I'm going to make it super big here because that way it's really obvious. How many spots are we going to move it? 3. But what direction? Right. Well, I'm hoping you said left, but that's the direction that we need to move in. We need to move in the left, to the left, just like Beyonce, right? 1, 2, 3. Sorry about the bad jokes today. And then, you know, what do I do with that, right? Now I got this like decimal floating out here. Well, we can just fill in some zeros as placeholders, okay? And then I usually rewrite it just so that it looks nice. So my answer is, and if you wanted to put a 0 in the front, you could, but it would be 0.00 and then 2, 3, 5, okay? So again, this is why I think it's important that we have this plus minus up here, just because I think that when you see this, you remember what direction to go. Using that information, let me write this guy on the board right below it. 1.4 times 10 to the 4th. Again, we don't have an extra value here, so we're assuming it's just a 0. What do I need to do? Turn it into an actual number or a standard format. So, how many times am I going to move? Let me make my decimal really big here first. How many times am I going to move the decimal? 4 times. Am I going to go to the right or to the left? To the right, right? It's a positive number. Positive, I'm going to the right. So I'm going to move it 1, 2, 3, 4. I know that doesn't look too pretty, but I kind of like to leave this on the board so that students see that I'm not like making any massive changes or do anything too crazy, but I do need to put in some filler zeros. And that's another reason why I make my loop-de-loops here so big and obvious, because I think that that helps the students and it helps me. It helps me see just how many times I need to move the decimal place. And then what do I need to do here? I need to fill those spots in. So my answer would be 14000. And if you wanted to, you could put in a comma like that. Okay? So we've gone through scientific notation. We've gone through a couple in standard form. Really the most complicated part of this, I believe, is just being careful with the decimals. Now there are books and sometimes you'll hear just, if you have a decimal one, just know that your times 10 to the something is always going to be negative. I'd rather you have a little bit more of an understanding of it versus just having these rules where you're just a robot and not really thinking it through. So that's why I like to draw the picture and then test your answers too. You know, if you write an answer in scientific notation and it looks like this, you know, maybe try it. You know, when I say try it, you know, try to read your own problem and say, oh, I'm going 1, 2, 3 times to the left, and see if you actually get the original number you started with. What I mean by that is, let's do this guy real quick right here. 6,435. The answer to that one was what? Number, decimal, number times 10 to the 1, 2, 3. So it was 6.43 times 10 to the 3. Now, on another note, sorry, some books will ask you to round some of these numbers. So like, because there's a 5 there, they'll say, well, you technically could round the 3 up to a 4. Okay? Some books do that, some books don't. All right? Just as a side note. But let's say I convert this to scientific. I'm so proud of myself. Can I check it? Well, you just kind of got to use the rules again and look at your problem and say, okay, well, my decimal's here. I'm going to make it really big and obvious. I'm moving my decimal 3 spots positive to the right. 1, 2, 3. So my final value here would be 6,430. Now the only reason I'm missing the 5 is because I dropped it when I did my scientific notation. But for all practical purposes, it's the same answer, okay? And so that is a nice way for you to be able to check your work. So I hope this is a good review for you guys. Post questions, you know, let me know if you want to know more about this. But these are some solid basics with this. And keep practicing. Talk to you guys soon. Thanks again for watching.